Hi, I'm John Orpin, and I'd like to welcome you to this presentation on StereoCore Photolog. It is an application that we have developed using photogrammetry to make light work of drill core logging. There are just 7 easy steps to success. In step 1, the core is photographed in the core tray. There are no special requirements, and as you can see, the camera can be handheld. Next, the photos are imported into the program, and then a rectangular wireframe is stretched across each photo and dragged into a polygon to match with the corners of the core tray, after which the program undistorts the photos. This processing produces an orthographic image of the core tray, which image is now perfectly rectangular and accurately calibrated for scale and perspective. In step 3, the core is logged using color-coded data markers to tag different features such as joints or lithological contacts, to pinpoint their position on the image and describe each in full by selecting their descriptor codes from a pop-up with drop-down menus, in which the lookup tables are fully customized to suit each project. In step 4, we don't have to work in the core shed. We can take the project back to the office, because now we are depth registering the core by drawing segment lines along each segment of core, also marking the natural fractures on the core so that we can measure RQDM accurately, and then we depth mark the core blocks. This is StereoCore Photolog, and the first thing we do is to select the segment line data marker. You can see that some of the segment lines have already been drawn on this image. I'm going to draw the last 2. That segment line at the bottom, and then I'll enlarge a bit to draw the last segment line. Along that segment of core, it's color-coded red for bottom side oriented core. Top side oriented core would be blue, and if it's no orientation, it's yellow. Next, we mark the natural fractures. At the moment, it's a red tick at the top of that line to denote that it's a mechanical fracture, so we change it from a mechanical to a natural fracture when it's a yellow tick. Let's just change this back to bottom side oriented core. There we are, we've had all the other natural fractures on this core marked already in yellow. And then the final thing to do is to depth register the core by depth marking each of the core blocks at the end of each of the drill runs. And that then enables us to automatically generate the core recovery log from and to the advance of 3 meters, total core recovered, the core loss gain, the solid core recovered, matrix rubble length. Matrix rubble is color-coded turquoise. The RQDM has been measured, the mechanical RQDM, and all the natural fractures and mechanical fractures for that run have been counted. That log is automatically generated. We're near the end now, because in step 5 we simply generate the logs by depth referencing the data markers. So to show you again in StereoCore Photolog, the data markers that we placed on the imagery in step 3 when we were logging the core in the core shed, you can show by ticking the boxes in the visibility panel on the left. And each of those now, the point logs and the interval logs, need to have the depths automatically added to the tables. And in order to do that, you simply go to Project, Snap Data to Segment Lines, and all the depths are automatically added to the log, as you can see, for the depth intervals and for the veins and point logs as well. The final task in step 5 is to measure the alpha beta angles for each of the different structures that have been intersected if the core is oriented. As you can see, the data markers now turn into lines which are perpendicular to the core, and you can adjust those lines using the 3 handles that are on each of those lines to create a half ellipse shape, and the half ellipse shape will then measure the alpha beta angle for the geometry of the shape measures the alpha beta angle for the structure. To demonstrate on a closed structure a vane, there's a vane that we've got in the core, and we match it with the handles of that structure to create the ellipse, and then the half ellipse shape is shown, and there the alpha beta angle is. But now we've got to generate the dip and dip direction from the alpha beta angles, and that takes us to step 6. All that is required in order to convert the alpha beta angles for each structure into their dip and dip directions is to import the borehole survey. So after the borehole survey has been imported, then the dip and dip directions are automatically interpolated from the alpha beta angles measured. And now to the final step, which is step 7, and that is just simply to export the project data. And in order to do that, we click on the Export Project Data button and choose the pages that you wish to export, either in an Excel format or as comma-separated values, and click on the Export button on the pop-up, and the file is automatically generated and saved, ready for import into any database for further analysis and the modeling of the data. So to recap the 7 steps, the first 3 steps, photographing the core, processing the photographs, and then logging the core by tagging features with data markers on the images to record their descriptors, can be done rig side, as there's no special requirement for any of those processes. The next 2 steps, 4 and 5, which is depth registering the core, followed by depth referencing the data, can be done away from the core and even by another person. And remember that the copies of the project can be made for detailed logging of the core as well by other experts in the core shed, and then these logs can all be merged together into one archive copy. Finally, import the borehole survey in order to convert any alpha beta angles measured on structures into dip and dip direction before exporting the project data in Excel or as comma-separated files, and for import into any database for further analysis and processing. Thank you.